Hello everyone. In this video we're going to explore the terrain tools in the RhinoLands interface. If we go to the Terrain tab, the first group brings together 3 tools for importing terrain data. The first one allows us to import topographic data from the selected land area. When we run the command, this dialog box opens up. In the central part we can navigate the map by dragging the cursor with the left click held down. And if we do the same with the right mouse button pressed, we rotate the view. We can search for a specific location by coordinates or by name. And we have shortcuts to zoom in and out and to reset the orientation to north. With the icons on the other end, we can switch between different navigation maps and enable the 3D view of the terrain, buildings, or roads. At the bottom, we have the Frame tool to define the area to import by drawing a rectangle on the map, along with the tool to remove the selection. Once we have the area defined, in the dialog on the right, we select the data we want to import. With Create Mesh, we will create a mesh labeled as a terrain with the photo of the scanned area. By creating a land's terrain, a terrain will be automatically generated using the elevation data we scanned. If we create buildings, it imports an approximate volume of the buildings included in this scanned area. And by creating roads, you import an approximate 2D of the road layout. In the first import, the center of the defined area will be placed at the document's coordinate center. If we do a second import in the same document, we can choose whether to keep the coordinate center from the first import or overwrite it with this checkbox. In the last part of this dialog, we can choose which data source to use, either JAXA or Mapbox. JAXA is more recommended for greater accuracy and relief, while Mapbox is advised for urban areas with less relief. And once we've made the selection, we click Import. And the selected geometry will be generated in our document. To see the mesh with the map image, we need to have it displayed in rendered mode. Each of these elements is generated in its corresponding layer, which will be created automatically and corresponds to a terrain layer, a building layer, and another layer for the roads. We can deactivate these layers as needed to work. Import Dem allows us to import a digital elevation model that contains information about the elevation of a terrain. When we run the command, we click the central button to open the File Explorer, and we can search for a file on our computer in any of these formats, like TIFF, PNG, TXT, or ASC. Once we've selected one, it might take a few seconds to load, and we can see a prioritization in the model. With the cursor, we can draw a rectangle to define the area to import into a model. We can import the topographic model in contours, meshes, or as terrain and select which layer we want it to be placed in. If we create a land's terrain, it will be placed in the terrain layer. This tool allows us to import geographic information systems. To do this, we need to have a file in shapefile format to import the geographic information or attributes we have, such as territorial boundaries or road maps. For the project we're shaping, we're going to create a terrain manually from drawing curves. Raising curves allows you to generate terrain from curves, lifting them according to an increase in height. It's useful for transforming contour lines or level curves into a 3D volume. To generate the terrain for this project, I have a series of topographic curves. If you don't have a terrain to work on, you can just create a series of parallel curves to test the following commands. As we see, all these curves are coplanar and lie on the construction plane, which is at an elevation of 0. So we're going to raise them. We select Raise Curves and enter the elevation increment between each curve. If I set a value of 0.5, each elevation will rise half a meter compared to the previous one, since I'm working in meters. We click on Draw Line and cross a line in the drawing that intersects with all the lines, from the lowest elevation to the highest. If we've made a mistake in the elevation direction, we can reverse it using the Invert checkbox. As we see in the drawing, all the curves start from elevation 0, but I know that the part we have already modeled corresponds to the elevation line of 165. And I have a total of 5 curves. Below this, since they increase half a meter per contour line, I input a negative value of 2.5 meters as the initial dimension. We apply it again, and now yes, the curve I know, which corresponds to an elevation of 165 meters, is at a height of 0 in the drawing. With the elevated reference curves, the Terrain tool creates a 3D model of the terrain. This command allows you to select meshes, curves, or points in the drawing. And it will take all the points from these reference geometries as elevation data to generate a terrain. I select all the curves, and we right-click or hit enter when we're done with the selection. And the terrain creation dialog appears with 3 tabs. In the first tab, we set up the visible material in the rendering mode for this terrain. We can specify that it takes the material assigned to its layer or choose a texture from our computer. If we open the folder to browse, we have some textures that we can use. The second tab configures the contour lines associated with the 2D view of this terrain. And in the field we have parameters to configure the triangulation of the mesh. We can adjust the cell size and the smoothness with which this mesh is generated. And if we check the base box, we can generate a closed mesh and set its height. We accept it, and this object has been generated for us. The terrain object is a lands object. The unique thing about lands objects is that they aren't just simple geometries. They are inserted as blocks that contain related information for later documentation, and they also allow you to switch their display from 2D to 3D. The tools we have seen for editing surfaces and solids do not apply to this type of objects. To modify them, we access their parameters from the editing panel. If we look at the editing panel, which you can open from the panel's menu, it shows us generic properties for the document. In the View tab, we have the option to visualize the representation of lands objects in 2D or 3D. The selected representation is applied by Active View. If I have the perspective view active and switch to 2D, it only changes the representation in this view. If we want all the graphic windows to sync up simultaneously, we check the sync box. Within each option we have different display modes, which only affect the graphical representation of the vegetation objects, so we will see it later, as well as the Document tab, in which the seasonality of the vegetation is configured. We also have a Geolocation tab, which allows us to assign a geolocation to the origin of the drawing's coordinates, meaning at point 0, in latitude, longitude, and elevation. So that if we document or reference any point in the drawing, it corresponds to real coordinates or elevation. Finally, in the Layers tab, we set up which layer each type of ANS element will be placed in by default. As we can see, to insert the terrain, a default terrain layer has been activated. We can select another layer for the next terrains we create since this one has already been placed in this layer. Or to pre-activate a specific target layer for some other element. And once the terrain is created, I can hide the curves I used to create it. And we'll see that this editing panel changes depending on which lens object we have selected. The white background area of the panel corresponds to the selection list, and at the bottom, we always find the properties or parameters of the selected object. With the selection made in the terrain object, we see the same followed by tabs that we configured when generating the terrain, and we can edit its parameters at any time. And to these tabs is added the General tab, from which we can rename the terrain, choose the color of the object or the layer for it. And we also have a checkbox that lets us simultaneously visualize the 2D and 3D representations when we have the view in 3D. In other words, we see the volume along with the contour lines generated from the terrain itself. We can edit the intervals of these contour lines, their color, or how often they appear. Now that we are looking at the 2D of this terrain, we observe that the index line, which was referenced as 165 meters, now takes a value of 0. I can edit this from the Geolocation tab. entering that the elevation at point 0 has to be 165 meters. To update it, we select the terrain and click this button to refresh. When selecting a terrain that hasn't been imported but generated from a reference, like in this case, we see all the geometry listed that is used to create this terrain. We can select curve by curve to view which input data it corresponds to. And we have options to temporarily activate or deactivate an input data or permanently remove it. If, after removing a curve from the elevation data, we want to add it again, or add new references for the terrain, we have the Add Contour tool, which asks us to first select which terrain we want. And then select the curve or point to add, and the terrain will be reconfigured, adding these new input data to the list. Each of these input data can be renamed and we can activate the visualization of their control points. If I activate the control points for this contour, when I select the terrain, I will visualize them. These points will be the same control points that the curve we selected for creating the terrain has. We can move any of the control points individually or move the entire curve. From the movement control arrow, which will appear at one of its ends. With this movement control arrow, we can move the entire set of points. We're going to look at different earth-moving tools that allow us to modify the terrain's topography in various ways. We have already seen adding contour to add a new contour line to a terrain. And with the boundary, we select closed curve to define a limit on the terrain. Visually, the terrain will be trimmed to fit the defined area, but this operation doesn't affect the earth-moving calculations and is completely reversible. For this command, we first select the terrain and then a closed curve that has already been created in the drawing. Now, when I select the same terrain, it lists all the terrain operations that have been carried out in the selection area. And limit appears, with options to temporarily disable, remove, or extract the curve. If I have deleted the original curve and at some point in the project I am interested in obtaining the curve that delimits this terrain again, I could extract it again. In the views, we also see their control points that we can modify interactively. We can also create interior boundaries, which would allow us to extract an inner part of the terrain without considering it in the earth-moving calculations. This tool, just like in the previous command, can take any shape, whether it's a polyline or a curved line. The hole tool creates holes or depressions in the terrain by removing material from specific areas. The hole is created from a closed curve that defines the area to be subtracted. In this terrain, I can subtract the contour from the previous modeling to flatten it out and at the same time, remove the thickness of the pavement. We need to have the curve created beforehand, and now I can select the terrain and the curve used. When it comes to selecting hidden curves for the terrains, the wireframe visualization mode really helps us see and select elements that would otherwise be hidden. The elevation of the curve is what will determine the depth of the hollow. Any terrain operation can be edited. We can move the height or position by looking for its handle. Or we can also modify the position of the control points. If we look at the editing panel, it has created a drop-down that lists the earth-moving operations we've been doing. By selecting it, we can rename this operation and edit the cutting angle on the terrain. By default, it's set to 90 degrees, but we can specify a different value, whether it's measured in degrees, as a percentage, or as a ratio. And we can see the fill option in the next command. With this tool, we perform a cut and fill operation on the terrain simultaneously. Depending on the height of the curve, the terrain will be cut in those parts. Let them protrude from the elevation of the curve and fill in any other parts that require it. If I have a closed curve at this point, where we see that half of the curve is buried in the terrain while the other half is above the topography, we run the command and first select the terrain. And now the command line is asking us to enter the angle, which we can modify later, and finally, select a closed curve. And we see how, on one side, it has lowered the terrain, and on the other, it has filled it in. If we select this operation in the editing panel, by default, the angle is the same for both operations. By clicking on the lock, we unlink them if we want to input different values. This is how we can achieve, for example, a 90-degree cut, meaning a straight cut in the terrain, while also keeping a smoother fill. With the extension box, we control the extension. If we look at the fill angle, it extends until it meets the topography. But if we specify a value here that corresponds to the length. For example, I'm going to indicate a length of 1 meter. The marked angle, which in this case is 20 degrees, extends to this equidistance of 1 meter. And from this point on, it won't respect the indicated angle anymore. Instead, it will try to reconnect with the terrain's topography again. When we have an operation that performs a 90-degree cut with the fill disabled, it is automatically renamed as a hole, unless we give it another name. When creating an earth-moving operation, a division in the terrain will also be created by default. These divisions allow us to control their color, layer, and also their material for rendering mode. If they are not convenient for us, we can always delete them. And if we want to extract them again, we select that operation and the option to split again appears. We also have tools to create paths. This command adjusts the elevation of the terrain based on the path of a curve. When we run the command, it first asks us, like before, to select the terrain. Next, it asks for the width we want the path to have, then the angle, and finally, to select the curve. In this case, it's going to be a curve, line, or open polyline. In its parameters, besides the Earth Moving tab that we already know, where we can adjust the slope or angle, we have a Path tab, where we can reset the width, modify the alignment of the path concerning the original curve, and choose from 6 different elevation modes. With the first one, the path takes the elevation of the curve and adapts the terrain to fit all the control points that this curve has. We can also make it adjust only to the elevation of the curve at the beginning and the end of it. But between these 2 elevations, it will create a smooth transition. As you can see, this curve has a third control point in the middle, which if I move it now, it is not taking it as a reference. Whereas if we were to take the elevation of the curve again, it would use this point as a reference for the terrain's elevation. We have the same option to create a uniform slope, adhering to the terrain's elevation at the starting and ending points of the curve. And there are also options to set a specific slope. With this option, a slope tab is enabled, and we can define the unit of measurement to enter the slope, such as by height, percentage, ratio, or angle. And at the bottom, it gives us the conversion information for the slope we indicate in different formats. Returning to the Path tab, in any of the options we can establish a maximum slope. If I want to ensure that the slope never exceeds 4%, I activate this box. And in any of the elevation methods, if at any point the slope is greater than the specified one, it will restrict this slope starting from the beginning point of the curve. There's an elevation method called slope by segment, which is only available when the original curve is a polyline. In this case, if we select this option, in the list, it subdivides the path by segments. The segments are defined by the control points of the curve, and by selecting them, we can assign a different slope to each of these sections or segments of the path. The slope will always be ascending from the origin of the curve to the end. If we wanted to ascend or descend in the opposite direction, we have an option here to reverse the direction of the curve. To continue with the project we're developing throughout the tutorials, we're going to prepare the ground with different slopes. For the next tutorial, I'll be modeling parametric civil engineering elements like a ramp, side stairs, and walls. I'm showing you a review of the project. In the next tutorial, we're going to model this entire part. So I'm going to use the Path tool to prepare the ground with different slopes where we'll place the ramps. First, I'm going to create a polyline that follows the entire path of the ramp. I position myself in the plan view and start from a point. Maintaining orthogonality, I create the first section, which will be a flat stretch of 3 meters, followed by the first sloped section. I'm going to give it a length of 9 meters and another section of 2, which will be the width of the ramp. I continue with a 90-degree turn and a value of 2 plus 1.4 plus another 2 meters. I come back with 2 more, followed by 7 ramps and 2 more. I turn again at a distance of 1 meter and repeat this sequence. When I get to the second side, I do segments of 2, 1, 4, and a final stretch of 2. I repeat the 9 for the last ramp and doi, a last section that will be the landing in front of the 3-meter stairs, just like at the beginning. I'm going to draw a second, shorter line in the final section, which will help me measure what height I need to cover with this ramp. The Terrain Elevation tool moves any object vertically until it meets the surface of the ground. If I select the curve I just created and elevate it to the terrain, it adjusts each of its elevation points to the surface of the ground. I'm going to use this to optimize the slopes. What I'm going to do is make it so that only the horizontal ramp sections have a slope, and I'll use the vertical sections as landings. To do this, measure the height to cover from the highest point of the ramp on the ground, up to the smallest, that is, between the starting and ending point of the ramp. I'm going to draw a line to help me with this measurement, and from the right view, using the Align Dimension tool found in documentation, I select one point and then the other. I move the dimension to the side, and it shows me the height I need to cover. To work with a value that will fit better when calculating the steps, since I'm going to make steps with a rise of 16 centimeters, I'm going to adjust it to a value of 1.92. I'm going to divide this value of 1.92 by 4 sloped sections, which gives me a height of 0.48 per section. Now, when I generate the earth movement with the Path command, I set a width of 2 meters, and in the command bar, if we're not interested in creating the terrain division, I can turn that off directly before selecting the curve. The first thing I'm going to do with the Path is align it to the right, correct its cutting angle to 90 degrees, and specify that it should take the slope by segment. To start, I select all the segments at once and set the slope by height with a value of 0. And then, set a negative value of 0.48 for those selected ramp segments. In this case, I'm working with negative values instead of reversing the direction of the path, because this way I make sure that the elevation of the starting point, which is the one in contact with the already modeled part, doesn't get changed. In the end, we should have this result, where we have a series of landings connected by 4 horizontal sloped sections. Before continuing, I'm going to center this path a bit by moving it from its handle. And then make 2 rectangles. One of them will help me extend the area of the central landing, measuring 3 by 5 meters. And a second one to generate an area to connect the ramp at its lower part, such as a walkway area. With these I'll do 2 cut and fill operations. I can give this first one a lower angle so that it blends more naturally with the terrain. As you can see, this earth movement operation affects the path operation. That's why in the editing panel, we have the option to move an operation up or down. If 2 operations can interfere with each other, the one that appears lower in the list, it is understood that it is the last operation carried out and, therefore, the one that will prevail over the others. I'm doing a second cut and fill for what will be the landing, and I move it above the path operation. For the terrain under the stairs, we'll edit it once we've modeled them. Going back to the Tools in the Terrain tab, Earth Movement Volume. It shows us the volume of earth removed and the volume of earth used for filling in the selected terrain. In order to document the terrain, we will see that we can extract the list to view in detail. The Division tool allows you to create the division areas that we have already seen previously without being linked to an earthwork, simply to be able to obtain its area in a list or to make a change of color or material for this area. And finally, we have the option to mark as terrain, which allows us to identify any geometry as terrain so that other elements, like plants, recognize this geometry as if it were the surface of the terrain and align themselves automatically on its surface. And raise terrain to vertically align geometry or objects to the height of the terrain surface or an object marked as terrain. And that's it for this tutorial in which we have seen the tools, one by one, in the Terrain tab. See you in the next tutorial with the tools for vegetation and hardscape elements.